Thank you so much for the introduction, Greg. And I'm very happy to be here today. This is my first time attending Stereoscopic Displays and Applications, and I have to say it's a great crowd, very enthusiastic people. I've rarely seen such a community, and it's my great pleasure to be here today. So yesterday's keynote was all about the history of 3D displays and the past. So today, what I'll try to do is convince you what I believe to be the future. So I'll start with an image of one of the first televisions. Was built around 100 years ago, and a modern television that we may buy today at Best Buy. And the electronics and optics have fundamentally changed, so has cable television and so on. But the viewing experience, the experience you have as an observer, hasn't really changed at all. We still watch 2D movies on a flat screen, and what we really want is to get 3D, to get all these depth perception cues and so on. So one of the main things, one of the main points to take home from my talk today is really to think about how we can change the user experience as opposed to building devices. And what we do at MIT is we try to do this using new kinds of optical arrangements for new kinds of displays by taking apart existing displays. So we don't make LCDs, we don't make electronics, but we disassemble existing televisions, we disassemble monitors, we use LCOS devices from head-mounted displays, projection lenses, and so on. We combine all of them in new ways, and then we add computation. So the computation is really the key for future displays. Greg said yesterday that it's very difficult to do something new in this space, in the space of displays, because many people that may have been smarter than us have looked at these problems for about 100 years, right? What's the promise of doing something new? Well, the promise is that we can use things that they just didn't have, such as computers. Today, we have high-performance computing at our disposal, so let's use that in a meaningful way to build different kinds of displays that people in the past just couldn't build. Now, the question is, how do we build meaningful optical setups that are well-suited for compression or computation? Because not every possible combination of hardware components is suitable for that. So we can look at nature and get some inspiration. Here's an image of a butterfly. This blue morpho butterfly has, if you look at the wings, at the structures under a microscope, it has these multi-layer structures that create diffraction, and that results in the butterfly appearing to have different colors as you look at it from different directions. So that's called iridescence. But we already see that there may be something there in these multi-layer structures, and as Mr. Gotoda just told us, that there has been a lot of work on these multi-layer displays also, because this iridescence is a view-dependent effect, which is something that we may be able to leverage for building 3D displays as well. Here's a picture of a hummingbird. Hummingbird flaps its wings so fast that over the exposure time of the camera, we can only see a motion-blurred version of these wings. We cannot see the actual wings. It's integrated over time. And that happens too in the human visual system. When we look at things that move faster than what we can resolve in our visual system, then perceptually, this is averaged or blurred over time. So this is an important effect that we can also use for temporal multiplexing in display design. And here's the last picture I want to show you. This is one of my favorite animals. It's called the mantis shrimp. It lives in tropical waters. And I'm not saying we should build displays that look like the mantis shrimp, but the key point here is that this animal has a very interesting and peculiar visual system. It has these two compound eyes mounted on stalks, and it has trinocular vision with each eye. So remember, we get binocular vision with two eyes. This animal can see 3D with a single eye at a very low resolution because it's a compound eye. But that's very interesting, and at the same time, some species are reported to have up to 16 different types of photoreceptors in their retina. So remember, as humans, we have 4 different types of photoreceptors. This guy can see 12 different colors and 4 different types of polarization states. And why is that important? Well, evolution has come up with visual systems that are highly adapted to their environment. And that's a message that we can take also to display design. If we want to design user experiences, then we need to build displays that are not necessarily good at everything, but that provide one experience or that are really amazing for one particular application. And that's something to keep in mind. So here's an example of a display we built in 2012. We call it the Tensor display. It's very similar to Mr. Gotoda's work on multi-layer displays. In fact, to get back to your question, there is some diffraction and moire visible in the display, but what you can do is just put a slight diffuser in the front, and you can account for that diffusion in the computational methods. So it's really a co-design of optics and computation. And when you look at the screen, what you'll see is a high-resolution 3D view of a scene. You can move around, but we use high-speed LCDs that all show different patterns over time. So when we take a high-speed camera, where we can see these strange patterns distributed over the front, the middle, and the rear LCD. But when optically overlaid and observed by the visual system, by a human that has a finite exposure time of the eye, this all perceptually fuses into a consistent, high-resolution 3D view. And it provides horizontal and vertical parallax. I should mention that at no point in this talk I will talk about stereoscopic displays. All of the displays that we're working on are multiview, which is what we call light field displays. So this is an example of a compressive light field display. And what's a light field display? Well, it's the extension of a stereo display to multiple views. So you and your friends can watch a movie, and everybody gets to see two different images with their eyes. So it's stereoscopic, but in addition, it also supports motion parallax, so that everybody gets to see the correct perspective. And for that to happen, the display has to emit a 4D light field. And a light field is nothing else than a collection of 2D images showing the same 3D scene from slightly different perspectives, as you can see here. So this is a collection of a few images showing the scene as the viewer moves left to right, up and down, in this case with full parallax. In order to create extremely good user experiences, however, we cannot just consider 5x5 views. That's not enough over a wide field of view. We need to consider hundreds of views. This is something that holograms can provide. For instance, if you had the chance to see some of Zebra's holograms, it's just an amazing experience over a large field of view. For that to happen, you really have hundreds of views in all different directions. But that's not only optically and electronically challenging, it's also a big data problem. So consider this example. We want to show 100 by 100 views, each one with HD resolution, streamed at 60 Hertz, which is really not outrageous. The bandwidth required to process this data is in the order of terabytes per second. So this is really a big data problem, in addition to being optically and electronically extremely challenging. So the way we attempt to address that is using a computational display approach. We'd like to co-design new optical elements or new optical configurations in combination with the processing algorithms, with high-performance computing, to bring down this data rate by an order of magnitude or so, and also relax optical and electronical requirements. So all of you know that there are a lot of depth cues in the human visual system. I don't have to repeat those in detail. There's binocular disparity, convergence, motion parallax, and so on. And we all know that stereoscopic displays today only support a few of those, and in addition require glasses. With light field displays, we really address this entire space, including accommodation, and we want to get rid of the glasses as well. So this is something that holograms can offer, and I don't argue that light field displays are the long-term solution. Holographic displays may very well be that. But it's not a short-term solution because the requirements on pixel density, pixel size, prevent these displays from being a short-term solution for the next few years. And all of you also know that people have looked at this for 100 years. In 1903, Frederick Ives invented parallax barriers by simply placing an array of pinholes or slits in front of a conventional 2D display in order to turn this pixel display into a ray display. Unfortunately, it's low resolution and very dim. We can also use integral imaging. It's also 100 years old. It's brighter than parallax barriers, but still low resolution. So most displays today, most light field displays today are still based on these principles. So the next generation of displays really should consider the co-design of computation and algorithms with the optics and electronics, but also consider the limitations of the human visual system. And eventually, we also need to consider how the observer or the user actually interacts with these devices. So all of these parts come together, and that's quite challenging because it's so many different components. So when I thought about, preparing this talk, I wanted to give you some lessons learned. I wanted to give you some key insights that we've made over the last few years that helped us develop a whole range of different display technologies. And we'll go through this in the rest of the talk. And I call it the structural formula for compressive display innovation. It's my crude approach to summarize a number of lessons learned here. And these include multiplexing, nonlinearity, compression, designing user experiences, the content, of course, and also the community aspect, and also keep in mind what's next. So let's talk about multiplexing. Most of you will be familiar with these techniques. And most of you know that we're really good today at building two-dimensional displays. Manufacturing technology has evolved to a point where we can cheaply and easily manufacture high-resolution, high-contrast 2D displays. But in order to turn them into 3D displays, we need to use a 2D display, modify it using additional optics, such as parallax barriers or lens-led arrays, and then we have a 3D display. Well, this is a type of spatial multiplexing. So you recycle your 2D pixels to be 3D rays or 4D rays. Is that a good idea? I don't think so. Let's look at the human visual system, and this is really just a first-order approximation. Looking at the sensitivity of human vision to resolution, we quickly figure out that the human visual system is very, very sensitive to display resolution. There's a reason why the display industry pushes for more and more pixels. So looking at the example of retina display, at a display with a distance of about 10 inches from your eye, the display has to support about 300 dpi to match the size of the cones, which is about 1 arc minute of a degree. And that is very high resolution. This is what we can achieve today, or at least a few companies can do that already. But if you consider multiplexing, spatial multiplexing, you would have to increase that number by orders of magnitude in order to get a retinal 3D display. And that's pretty much impossible today. On the other hand, the flicker fusion threshold, the temporal resolution of the visual system, is much lower. We can only resolve about 20 to 60 hertz, depending on the lighting condition. So existing spatial light modulators, such as LCDs, DMDs, and so on, already support hundreds of megahertz, hundreds of hertz, or even kilohertz. And that is substantially faster than what we can already resolve. So why not use temporal multiplexing instead of spatial multiplexing to improve or add 3D-ness to our displays? So that's much easier. So how can we do that? We can also combine spatial and temporal multiplexing. For instance, here are conventional parallax barriers. You have one layer with the content, one layer with an array of pinholes. And in 2007, some researchers from Korea came up with this idea of using time-shifted parallax barriers. So if we can only shift these pinholes at a very high speed, we can get a high resolution by temporal multiplexing, but it's still very dim. So the human visual system will average over all these images, just like the hummingbird I showed you earlier. So the lesson here is, if we can use temporal multiplexing, we should probably do that, because the human visual system is not as sensitive to time as it is to resolution. So here's one of the most important lessons learned in the last few years. That is, we need to build optical systems that provide nonlinear pixel interaction and coupling. So what does that mean? What's a nonlinear pixel interaction? Well, let's take a look again at parallax barriers. Well, we have a bunch of rays emitting from this display, but as I said, mask 1 in this slide is actually a conventional 2D display. Each pixel emits light in all directions. And then mask 2 is basically capable of blocking some of that light. So that's a key ingredient here. It's capable of blocking the light. So if you write that mathematically, it's very simple. It's just a multiplication of one pixel by the other pixel. And as easy as it may seem, this is a nonlinear operation. It's a multiplication. So if you were to write this as an addition, it would be linear. And you cannot block anything. Right? That's a key difference. Most volumetric displays, unless you use special tricks, cannot block any light. So you cannot really support occlusions, as I said, unless you use any sort of special tricks. Same with layered transparent OLEDs, for instance. You cannot block any light. That's a linear effect. So my argument is that linear optical image formation is not very well suited for creating the degrees of freedom that are necessary to build 3D displays. You may disagree, but here's an example. Even holography is a nonlinear effect. Consider a thin refractive layer, the hologram, that is illuminated by a coherent plane wave. Van Huygens principle tells us that we have this wavefront that emits from the hologram, and that's a complex wavefront, right? It has a phase and it has an amplitude. So when we look at it as human observers, or we just put a screen in midair, what we'll perceive is the intensity. And the intensity is the squared magnitude of the complex field. What that means is you take the real part of the transported field and you square it, and you sum up the imaginary part as well. So it's a sum, but the square really adds a nonlinear term here. So holograms are linear in the optical field, in the complex domain, but they're nonlinear in the perceived intensity. And that's a nonlinear effect. Let's do a very crude simplification here. We all know that holograms are not rays, but let's just look at a single ray emitting at some position on the hologram into some direction. We can use the Wigner distribution function to get an approximation of that. And I don't want to go through the equations here, but if you look at them, what you'll see is that the emitted light, or the emitted radiance at some point in some direction, depends on all other points on the hologram. They're all coupled by some type of a Fourier transform. So that means not only do all these pixels on the hologram interact in a nonlinear manner, they're also all coupled. And this coupling is a key component of the 3D effect that you can achieve with holograms. But you don't necessarily have to provide this type of coupling. In fact, you can provide any type of coupling that may give you more degrees of freedom to get a 3D display. So now I'll show some work that we presented at SIGGRAPH in 2011, which is very similar to Mr. Gotoda's multilayer displays. This is a multilayer extension of conventional parallax barriers. So instead of having 2 layers, you have K layers. So each ray that is emitted by this device is the product of all the pixels that it intersects along its path. So that it was 1 pixel per layer. And again, that's a multiplication, so it's a nonlinear effect. Each pixel in return will affect multiple rays. So all these pixels and rays are somehow coupled. And this coupling is different from what you see in holograms, but there is certainly a coupling. And these two components together, the nonlinearity and the coupling, gives you the degree of freedom of creating 3D images that support occlusion, that support specularity, that support horizontal and vertical parallax, and many other effects that you cannot get with conventional volumetric displays. Agreed, it only works over a limited field of view and within a limited depth of field. But you can also increase the contrast. So in 2012, we introduced the Tensor display at SIGGRAPH. And one incarnation of the Tensor display is a multi-layer LCD version of the simple stacked transparencies that we used for layered 3D. So layered 3D is really something that you can build at home. You just print it with an inkjet printer. Here we disassembled some liquid crystal devices and stacked them up, and then we have a single backlight illuminating them. This is what I showed you in the very beginning. What you see coming out of this device is a high-resolution 3D view of a scene, but the individual panels are high speed. So we can multiplex different patterns over time and over the different layers to create this 3D effect at a significantly higher resolution than what parallax barriers can provide, and also at a higher brightness. So we showed this actually at SIGGRAPH in 2012 in Emerging Technologies. If you had a chance to see it there, that's great. We also have it in the Media Lab. So if you're close by, if you're in the Boston area, you should come by and take a look. In the same paper, we also introduced a different optical configuration that can be driven by the same mathematical framework. And that looks like this. We basically have two LCDs that form a sandwich with an array of lenses in between. So it's kind of related to Mr. Gotoda's work again, but we already introduced this with just two layers and these lenticulars in between. The good thing about this particular architecture is that the thickness of the device we built is only marginally thicker than the monitor that we used to disassemble. So we just took a monitor apart, removed the LCD, took another monitor apart, and reassembled all the components, but the thickness of the resulting device is almost the same as that of the monitor we disassembled. So how does the nonlinear interaction and the pixel coupling come into place here? Well, again, you have a multiplicative effect between pixels on different layers, and through the micro lenses here, you have a focusing effect that couples different rays on different pixels together. It's a different coupling effect than simply multi-layer displays, but it allows you to get a very thin form factor and works quite well in practice as well. We also use time multiplexing so that a human observer would perceptually average a number of frames here. So here's some images of the prototype we built here. You can see the 3D effect on the lower left. On the upper left, you can see a rendering of the scene from above. And what you see is that the red fish and the blue fish really stick out to the front and go out to the back of the screen. So virtual objects can significantly extrude from the physical boundaries of the device. And that's something that's challenging to be achieved with conventional volumetric displays. On the right, you also see a comparison between our approach, which is on the top, and conventional integral imaging, which is just the lenslet array on the rear screen. And you can see that for the conventional approach, every lenslet turns into 1 pixel. So the resolution is very low, which is what I already said earlier. And with our approach, you can basically get the resolution back with the additional LCD. So you can get high resolution and a 3D effect. There's some intensity variations remaining from the off-the-shelf components we used, but these could probably be engineered out. Remember, this is built by grad students in the manner of about 3 weeks, or basically 1 grad student and I. So this effect also works for objects that stick out of the screen. So here's another example of a T-Rex where we see is basically 6 time multiplex pattern integrated together for each of the frames. So again, you see a high resolution view of the T-Rex, but what we actually show on the panels are these high frequency patterns that change over time, but when optically overlaid and observed by a human, they all fuse together into this view. And what's particularly interesting here is that these patterns almost look like noise, but really it's not noise. It's all the information packed up in time-varying structures that especially form around depth discontinuities and other structures. So in 2011, we also introduced a different approach, and this goes back, we're still talking about nonlinear pixel interaction here, right? So far, we've only considered multiplication. The interesting part about this multi-layer device, although it looks very similar to the Tensor display, is that we use 4 LCDs, but only 2 crossed linear polarizers around the entire stack. So what that means is that, say for the example of 3 layers, we remove the color filters, we remove the polarizers, except for 2, and what happens is optically, the brightness, of course, is significantly enhanced compared to having all these color filters in there and the polarizers. But what's more interesting is that each ray traveling through the stack will basically be rotated by the pixels. So the pixels act as programmable polarization state rotators that you can control on a per pixel level. So a light ray is linearly polarized by the back polarizer. And then every time it hits a pixel on one layer, it gets rotated a little bit more and more. And then on the front layer, it passes through another polarizer, and the interaction between this polarization rotation state and the intensity, which is what you observe, is nonlinear. It's given by the physical law, the Baer-Lambert law, which is a periodic function, sine squared, basically. So that's also a nonlinearity, which is significantly different from a multiplication. And then the screen looks like this with the front polarizer removed. You don't see anything. As you place the front polarizer in the screen, this polarization field that comes out of the screen, all these rays having different states of polarization rotation are optically converted into intensity. So you see an image, but you can also move around the screen and you get this 3D effect. So you can see parallax, again, horizontally and vertically. We do all the computation that I haven't talked about in real time on the GPU. And then for color, we envision field sequential color. We strobe red, green, blue in quick succession. In our lab, we built the grad student field sequential color version, which is basically putting different color filters in front of the screen and digitally combining those images. So the message here is that we need to design optical systems that provide pixel coupling and nonlinear interaction, if possible, because that gives us more degrees of freedom in the computation. And this is something when you go into the microscopy domain, over the last 10 years or so, nonlinear microscopy has really emerged as techniques that can do many more things that we can do with conventional microscopy. So two-photon microscopy versus confocal microscopy and so on. So we need to think about the same kinds of patterns to build the displays of the future. The third point I want to mention is compression. So let me start with a question. Which of these two light fields do you think is more compressible? Here, first row. Take a guess. A, that's right. That wasn't very difficult. All the images in the light field are almost the same. We look at the same 3D scene. Yes, the objects move a little bit depending on the parallax, but it's still the same objects. So there is a lot of redundancy in that data. And the main message here is that we need to somehow leverage this redundancy to build higher resolution displays. And in fact, it turns out we can do that using these stacked layers or other optical components. We can use, in fact, any kind of combination of multiple stacked layers of transparencies, LCDs, uniform or directional backlights, lenses, and so on. All of these combinations may provide some type of a compressive optics basis. What does that mean? It just means that there are fewer pixels in this optical arrangement, that there are rays in the light field. Now the problem is we need to figure out how to approximate our 4D light field with this optical configuration. And for that we need display adaptive compression algorithms such as computed tomography or low-rank factorizations. So we really need to leverage applied mathematics and high-performance computing to compress these light fields into the pixel states that are available from the display. And if you think about JPEG image compression, it's very similar. JPEG is represented in the discrete cosine transform because you need much fewer coefficients to represent it there, so you save storage space. We can do the same thing by building an optical DCT basis, right? And then when the human observer looks at the screen, he acts as a decoder. So we computationally encode the light field, we compress it, and the human visual system decompresses it. So that gives pixels a break. We can use applied mathematics such as sparse optimization, low-rank factorization to give us direct benefits for the optics and the electronics. Examples include we need fewer pixels, we can relax the refresh rates of the displays, we can get thinner form factors, and we can get other benefits by shifting some of the optical and electronical design complexity into the computational domain. So why do you want to do that? Because computation gets faster, quicker than electronics and optics. So let's look at the timeline of these kinds of compressive displays. Well, we started with parallax barriers, then we moved to time-shifted parallax barriers, In this case, you shift these pinholes over time at a speed that allows you to perceptually integrate over a number of frames. And that achieves a higher resolution, but it's still very dim. Then in 2010, my colleague Doug Landman introduced what he called high-rank 3D. So the idea here was that instead of using pinholes on one layer and the content on the other layer, we can actually use content on both layers and thereby increase the brightness because we don't block most of the light. We can also use time multiplexing here, but in order to determine the optimal pixel states, we need to use formal optimization. And in this particular example, we need to use non-negative matrix factorization. We extended parallax barriers to multiple layers, which we call layer 3D, using this nonlinear pixel interaction and coupling. And it turned out that the algorithm that gave us the best pixel states for a given light field was computed tomography. I'll talk about this in a second a little bit more. But you can see that different optical configurations require different algorithms. So that's something to consider as well. With tensor displays, we basically provided a mathematical framework that unifies all of these multi-layer approaches, time multiplexing approaches. And in fact, you can also include all different kinds of optical elements here. They will just redirect the rays. But it's a mathematical framework that applies to all of these. And we identified that one optical configuration that we believed was the most commercially viable because it's very thin. So the conclusion here is that we need to design optical systems that support compression. Not all optical systems do. If we need to address every ray in the light field separately and in isolation, that is not a compressive approach. And then the fourth point I'd like to make is that optimization or high-performance computing, both of these, the algorithms and the implementation of these algorithms, are a key component of displays today. We already saw that in yesterday's talk by Andrew Jones. Rendering different kinds of sampling techniques will be required for unconventional optical solutions. So here's, going back to one of our approaches, layer 3D, we already saw that this can be built with simple inkjet printed transparencies. We really just use an office printer here. We stack those layers up. You can look at it and get a 3D impression. Well, as I already mentioned, that the algorithm that's being used to generate the pixel states are usually computed tomography algorithms. So this is something that's normally used in medical imaging. So how does that relate to 3D displays? It's not clear, right? But for those of you who don't know how computed tomography works, a simple introduction is that patient goes to the hospital, goes into the scanner, there's an X-ray illumination source, and all these X-rays are attenuated through the body. And on the other side, there's a sensor that measures the accumulated attenuation through the body. That scanner rotates around the patient, and then the computer automatically figures out what was inside without us having to open the body, right? So that's a non-intrusive technique, which is very nice if you, well, yes. So our 3D displays work in a very similar way. We have this volume that is basically a discrete set of layers. And we have different eye positions from which we want to see different views of the light field. So now that's the same problem. We have these different perspectives or projections in computed tomography, and we need to figure out what is the volume that will result in these projections. I don't want to bore you with the technical details too much. Here's just an overview. We have a sliced up version of our device. You have an attenuation volume that's approximated by a few discrete layers. You have some virtual objects that stick out of the screen to the front and to the back. And what you want is you want to figure out, which pixels states to show. So we represent these virtual objects as a light field, here seen in 2D. And you need to establish the mapping between the physical rays that emit from the device and the rays in the light field, right? And these are given by physical laws on the upper right. So there's not much we can do here, but we can reformulate these equations and basically end up with a linear equation system that we can solve. So this is really just solving AX equals B, given some constraints. But you just need to establish this mapping between your light field, which is the rays you want to see, the physics of what actually happens, and then you need to use the computer to automatically solve this. Turns out that this polarization field display that I showed you earlier is optically very different because it rotates the polarization state of the pixels. But you know what? It turns out that the solver we can use to compute all these pixel states is the exact same thing. It also uses computed tomography. It solves a linear system that is subject to different kinds of constraints and that results in completely different kinds of pixel states, but the solver that we can use here is the same thing. Again, I don't have the time to go into detail into all these solvers, and I think this is outside the scope of this talk. I just want to give you an overview of the kinds of solvers that we use. Here's a different approach. We have a light field with horizontal-only parallax showing the teapot. We have a two-layer display. This is basically a generalized parallax barrier display. And as I said earlier, every ray in this light field can be represented as the multiplication of one pixel on the rear screen and one pixel on the front screen. So the set of all possible rays is basically the outer product of the patterns on these two layers. So that's a matrix that you can see on the right. And as we know from our undergrad algebra class, the outer product of two vectors is always rank 1. So what does that mean for displays? It just means that we have limited degrees of freedom, which result in limited field of view, limited depth of field, and limited capabilities of creating occlusions and other view-dependent effects. But by using time multiplexing, we can get a higher rank approximation of our target light field because we perceptually average over all these frames. And we can use formal optimization to find the optimal pixel states, not only for multiple layers, but also over the time, right? And we don't actually need to do anything. We just throw in the light field, and it automatically gives us back our pixel states. We can extend this to multiple layers, and in this case, each ray is affected by one pixel on each of the layers, and that creates not a matrix, as for the case of two layers, but a tensor. Tensor is the multilinear extension of a matrix. In the case of 3 layers, we basically have a 3-dimensional volume. For 4 layers, 5 layers, this is a higher dimensional space. But we can represent our light field in this space and use the same factorization techniques. We can take our target light field tensor, decompose it into a set of rank 1 tensors that will be displayed at a high speed, perceptually averaged, and results in a higher rank approximation of our target light field. So if you're interested in all the math, you can read the paper, but the message here is that this is a complicated nonlinear problem that we can solve using some iterative approaches, but the mathematical operations directly map to operations that are supported in hardware on the graphics card. So this is multiview rendering in particular, and projective texture mapping. So just using these 2 operations and a few more, you can implement these update rules on the GPU in real time. And my knowledge of GPU programming is somewhat old, so I use OpenGL and CG, which is already deprecated, and I can still make it work in real time. So if you had a software engineer who's really skilled at graphics programming, this may even be able to run on mobile devices using some of the latest mobile chips. So let me show you what these optimization algorithms actually give us. Well, we have a target light field that contains a couple of bunnies. We want to see bunnies that come out of the screen to the front and the back, say, for instance, with 3 stacked layers. So the green bunny comes out to the front, the yellow one goes to the back. The algorithm automatically computes these patterns that we can directly show on the LCD, and they change over time. When optically overlaid and perceived with the human visual system again, we can see a consistent 3D view. And again, the conclusion here is we need to use formal optimization to find the optimal pixel states. So the next topic ties back to the very beginning. We need to design user experiences. So the audience today is probably the world's experts on 3D displays. So let me ask you something. What do you think is the killer app of 3D displays? And we're going to start with Greg.
Television and video games.
Television, okay. So watching movies. Okay, let's just list a couple others that immediately come to mind, which is medical visualization, scientific visualization, computer games. I mean, I'm sure we can come up with a list of 10 or 20 applications right now. But is that really the killer app? I don't know. But I think what we need to do is design experiences, not devices. And this is, for instance, what devices like Leap Motion and Microsoft Kinect do. They don't sell a device. They sell a user experience. So this is what we need to keep in mind as well. And I think it's good that this conference is called Stereoscopic Displays and Applications, because this is basically the application part. So one of the things so now I'm getting to the point where I show you some unpublished work, but hopefully you can find this online soon. Here's an approach where we try to design an experience. Say I take off my glasses and my eyes have visual aberrations. I can't focus on the screen anymore. Wouldn't it be nice if the screen could correct my visual aberrations for me? Right? So show me a 2D image within the focal range of my eyes without me having to wear glasses. So in fact, we can do that using 3D displays. So in this case, we're not showing a 3D image to a viewer. We're actually showing a glasses-free 2D image. So that sounds crazy, but it basically allows us to remove the 2D image from the physical device and show it outside the form factor of the device to allow us to give us this glasses-free 2D experience, so we don't need to use our glasses. And I'm going to show you a video here of our prototype. The prototype is basically a parallax barrier display. It's just a printed mask that is put on an iPhone here, and we use a camera that's defocused, so it simulates a viewer that cannot focus on the screen. And on the left, you see what a normal defocused image would look like, and on the right, you can see how we can compensate for that and still show a sharp 2D image on the screen. There have been a few approaches in the last few years, but those are actually not very high resolution or not very high contrast. So we can get high resolution, high contrast images with a very simple optical design. You can see that on the right. It's just an iPhone with the parallax barrier that we just removed, so you can see how defocused it is here. And if we place the parallax barrier back on the screen with a little bit of alignment, we can actually bring that image into sharp focus. So this basically ties back to supporting accommodation depth cues with a 3D display. But we don't necessarily always need all of accommodation, stereoscopic depth cues, and so on. I mean, in this case, it's desirable to be able to correct both eyes simultaneously, and this is what we did here. On the upper left, you see the target. On the upper right, you see what you normally see with the defocused eye. And on the right, we place two cameras observing the prototype from different directions that correspond to the interocular distance, and we can correct that as well. So all of this is basically computed automatically in software also. So I can't tell you too many details, but the interesting thing here is that we cannot only correct for defocus and astigmatism, but we can also correct for higher order aberrations, such as trefoil, coma, and so on. And this is something that's even difficult to be done with glasses. So maybe in the future, displays can not only correct our vision without us having to wear glasses, but they can also do that better than conventional glasses. And the message, again, is let's design experiences as opposed to devices. So one thing I've noticed at this conference is that there's a very strong community aspect here, which I really like. And in fact, last year I've tried to create a blog. I'm not a web programmer, so this was my first approach to creating a blog. And I actually want to share all of these insights and the construction plans for all of these displays. So we have this blog. It's called displayblogs.org. So I encourage you to go online. We have instructions how to build the optics, how to disassemble LCDs. We have source code online from MATLAB and OpenGL. We have data sets online of light fields. And we actually, at MIT, have a course on computational optics where we give this as an assignment to the students, where they basically capture their own light fields with their cell phone, then they run the solver, they print some transparencies, and we give them some pre-cut acrylic sheets, and they just basically build their own 3D display. So you can do that too, And in fact, I would like to encourage you to contact me if you'd like to share some construction plans yourself. So this kind of blog only lives by the participation of everyone. So if you have something to share, like how to build a volumetric display or how to build any kind of display, please contact me and I'll let you write your own blog entry here. So that'd be great. So let's share all of this knowledge. Content is key. For 3D displays, as you all know, we kind of need to distinguish between live action content that's captured in the real world and rendered footage. So consumer light field cameras seem promising, as do camera rigs for capturing live action content. In fact, Lytro came up with this consumer light field camera. They sell it as a device that allows you to refocus the images after you captured them. The technology is the same as integral imaging. You basically stick a lens-lit array onto a sensor and turn the pixel sensor into a ray sensor. So that comes at the cost of reduced resolution, just like the displays. And many of the lessons that I told you earlier, like nonlinear processing, compressibility, and so on, can equally be applied to capturing light fields. So last year at SIGGRAPH, we presented the first compressive light field camera that can capture a single coded image and recover the full resolution 4D light field. And for that, we introduced a new basis that represents natural light fields very sparsely, and we also presented a very simple optical design that just uses a coded mask in a regular camera, so we can capture an image and recover the light field. Here's our setup. I don't think I have enough time to really go into the detail, but we use an LCOS device, a conventional camera, and that simulates a virtual sensor with a coded mask inside the camera, between the sensor and the lens. And then we can capture images or even videos. Each image recorded by the camera looks like this. It's kind of, dappled. It's optically coded. It has some of the rays blocked and others not. And then we run a reconstruction and get the 4D light field back. So right now we face a lot of optical challenges because these LCOS devices are pretty low resolution that we are using, and there's a lot of directionally dependent color effects and so on. So the quality is not HD yet, but it goes in the right direction, I believe. We also work on rendering algorithms. So normally, if you want to talk about synthetic data, what you do is you render the entire 4D light field, then you apply your algorithms to it, and then you display it on your device. So that's the conventional pipeline. Render, optimize, display. But that's highly inefficient because, as I showed you in the very beginning, we need to actually consider trillions of light rays. So it's very expensive to render all of these, and then we need to apply nonlinear optimization to process all of these. So we also proposed an algorithm at SIGGRAPH last year that does all of that in an integrated way. So instead of rendering the whole light field, then optimize it, and then display it, we can just shoot a few samples and render only a few rays, run a small-scale optimization, and then go back and forth in an iterative way. And the outcome of that is that we only need to render and optimize about 1 to 3% of all the rays that are there. So we save a lot of time to generate images that look undistinguishable to a human observer. So it's important to keep that in mind, the synthetic content generation, live action capture, and so on. So the content is crucial, but we need to figure out better tools of how to capture it and how to render it. This is all multi-view, right, and not stereo. So what's next? Let me show you some glimpses of what we're working on these days. Well, as I already showed you earlier, we're particularly interested in accommodative depth cues. That means the eye can focus inside the screen. So for that to happen, we not only need to show different images to different eyes or show different images into different directions, we actually need to show different views into the same pupil. So it's like stereo for one eye. You need to show different images into the same eye. And that will allow you to create accommodation. And we did that by introducing this high angular resolution backlight. It's very similar to some of the devices that Neil Dodgson and Adrian Travis already built in the 90s in Cambridge. In this case, we have a big lens, an LCD in front of the lens, and then another LCD somewhere else. So that gives us a very high angular resolution. But we also use these factorization techniques to get an optimized image brightness and find these optimal patterns. In addition, we can use viewer tracking to really only consider the light that directly goes into the pupils of an observer. If you imagine me being the display, you can just shine these view cones directly into the eyes of the observer. And you don't need to consider the rest because nobody's looking there. Okay, let's see. Okay, I just want to skip to the results here. So on the upper right, you can see some pictures of an initial prototype we built, and the patterns that we show on the bottom, compared to parallax barriers, it's significantly brighter. Right? You can just show each view in a sequential manner, but that's optically very inefficient. Right? So showing these different patterns that, again, are computed with very similar algorithms that are described is optically more efficient. And then we can get binocular cues as well as accommodative cues here using these projected view cones into the eyes. So in this case, we just used a camera that had very similar aperture settings as a human eye and filmed it from two perspectives. Here's a different example where we have a shark and we focus back and forth, and we also move the camera in front of the display. So we can support accommodation, binocular disparity, and motion parallax. But I mean, the quality is, of course, not as good as what we can achieve with stereoscopic displays today. We can also look at other display characteristics. We don't just need to build 3D displays. We can also build super resolution displays or high dynamic range displays, because these are all the characteristics that are important for displays. And it turns out that you can use very similar display architectures for super resolution display, just like what I just showed you. So here we build a prototype that uses two LCDs, just like the high dynamic, the HR3D or conventional parallax barriers, where we put an additional diffuser on top of the screen. And what that allows us to do is create a higher pixel resolution than what you can achieve with the panel itself. So again, we use factorization techniques. We show time-changing high-frequency patterns on the individual LCDs. We optically overlay them, and then we get a high-resolution view. So here are some results. These are not as good as I'd like them to be. The theoretical limit in terms of super resolution you can achieve is you can get 4 times the resolution that you can get from one panel with the 2 panels. So here you can see left is the conventional, or both are filmed from the prototype. So you get a bit of loss of contrast there, but this is something that could be solved. The most interesting part about this kind of a display is that it's very flexible. We basically have a dual layer LCD display with a diffuser on top. If you have the diffuser on, you can have a super resolution 2D display. If you have an electronically switchable diffuser, you can just turn it off and you can have a glasses-free 3D display. And at the same time, you can also show higher contrast 2D content. So without changing the hardware, you can support different display modes, such as super resolution, glasses-free 3D, and so on, by simply changing the software, the algorithm that drives this device. So how could that look? Well, it could look like this, where you have kind of like a tablet, and if you look what's inside, you basically have 2 LCDs stacked up, or an LCD and a directional backlight. Then you have multi-touch on top, as well as an electronically switchable diffuser, and that device could provide all these different experiences, and it could actually adapt to the application that you're using it for, right? And this ties back to the mantis shrimp I showed you earlier. We don't need to build a single display that works in all different conditions, but we need to build a flexible display that can adapt to particular applications. And that brings me almost to the end. The last thing I want to show you is a 3D projector that we recently built. It's a glasses-free 3D projector. This is a prototype device. We use conventional optical elements, projection lens, in combination with a new type of a screen. So the projector generates a light field inside, projected on the screen, and it does so using two LCOS devices, which is the same as these two stacked LCDs. So now we are just basically looking directly into the projection lens, and we can see these high-frequency patterns run at 240 hertz. This is a high-speed camera filming the individual patterns at 1,000 frames per second. So we can see that they're really synchronized with each other and also with the backlight. So the backlight strobes at 240 hertz as well. The screen amplifies this angular range that is emitted by the projector so that when you look from one side through the screen, all the angles are expanded. If you turn around, you basically get this minifying effect. So that allows you to freely move within a much larger field of view on the other side of the screen than just over the size of the projector aperture. And again, looking at some results here, the parallax we can get right now is somewhat limited, but you can clearly see the effect. So these are some initial results we got. Clearly need to improve that. But this brings me back to what I just mentioned for the super resolution display. We can build devices that can adapt to the particular application. So we actually showed that this projector can, with a conventional screen, can also achieve super resolution. So when you just project on a regular wall, you can get a 4 times the resolution and a higher contrast that you can get with a conventional projector. Or when you use it with our screen, you get the 3D projection. So that brings me to the end. I talked about all these things, multiplexing, nonlinearities, compression, and so on. This is something to keep in mind when you design new kinds of displays. And I'd like to thank all my collaborators, especially Matt Hirsch and Doug Lippmann. All the code instructions are online, and I hope we have time for a few questions. If not, we can take it into the break. I'm sorry.